Hello, this is part D of the Chapter 9 lesson. In this part we're going to talk about one of the most commonly used statistical techniques that you will see in the journal readings, and that's the idea of logistic regression. Now, logistic regression is similar to linear regression that we've been talking about in the past couple of sections, except that the outcome in logistic regression, the outcome we also call the dependent or the response variable, that outcome is dichotomous. Now, dichotomous variables are something that we talked about back in chapter 2 and 3. Dichotomous means that we have one of two values. That's what the di means. So examples could be a variable that's either a success or a failure, or a yes or a no, or a 0 or a 1. So if we ever have a case where our outcome variable or our response variable has just one of two values, then we could maybe use logistic regression to analyze our data. Logistic regression is also called a logit model. Now, logistic regression is similar to linear regression in the sense that we're going to get a regression equation and coefficients and we're going to have p-values, but there's one fundamental difference. In a linear regression equation, we use that to predict the value of a variable, and we illustrated how to do that in the last couple of sections. In a logistic regression equation, we're not going to use it to predict the value of a variable. Instead, we're going to use that regression equation to predict odds and an odds ratio. Now, odds and odds ratios are something that we introduced back in Chapter 3, and we talked about them again in Chapter 7 when we talked about confidence intervals. But let's briefly review the idea of odds and odds ratios. So from Chapter 3, we defined odds as the number of events divided by the number of non-events. And odds we could think of as a measure of how likely something is to happen. Similar to a probability, but a little different way of measuring how likely it is to happen. Okay. Now, in an odds ratio, we can use this to compare two groups to each other. And so as an example from Chapter 3, we had this data, which give the results from 3,782 people. From each person, we recorded whether they have hypertension or do not have hypertension. And then we recorded whether they have cardiovascular disease or not have cardiovascular disease. So for instance, this says that we had a total of 2,942 people without hypertension, and we had a total of 369 people with cardiovascular disease. These numbers in the middle, for instance, this number means that 181 of those people without hypertension have cardiovascular disease. 659 of those people with hypertension do not have cardiovascular disease, and so on and so forth. And so we can use an odds ratio to compare the likelihood of each one of these groups getting cardiovascular disease. So to use this definition to calculate the odds ratio of cardiovascular disease in hypertensives versus non-hypertensives, we're going to calculate the odds of the exposed group getting cardiovascular disease. In this case, the exposed group is our hypertensives, and divide it by the odds of the unexposed. In this case, the unexposed is our non-hypertensives. So the odds of the exposed group getting cardiovascular disease is the number of events. That's the number of hypertensives with cardiovascular disease divided by the number of non-events. That's the number of hypertensives without cardiovascular disease. And then the denominator is calculated similarly, but for the non-hypertensives. And so we do that arithmetic and we get an odds ratio of 4.02. Okay. So our odds ratio is 4.02. What does that mean? We would interpret that by saying the odds of having cardiovascular disease are about 4.02 times higher in people with hypertension as compared to people without hypertension. So having hypertension significantly, or appears to significantly increase the likelihood that you get cardiovascular disease. Okay. So again, to kind of summarize what this example illustrates, is that an odds ratio is used to compare one group to another. It measures just how much more or less likely one group is to get a disease than another group. And when we calculate an odds ratio, there's always a reference group. We're always comparing one group to another group. That other group is what we call the reference group. In this example, the reference group is people without hypertension. Okay? So we're always going to have a reference group, and what that reference group is varies from situation to situation. Another thing to remember, and this is a point that we made back in Chapter 7, is that an odds ratio equal to 1, or very close to 1, means that there's not a lot of difference between the two groups. If the odds ratio is 1, then that means that the odds in both groups are equal, and so there's just not that much difference between the groups. So keep that in mind when we're analyzing our results a little bit later on. Now, let's look at our first example dealing with logistic regression. Now, this is example 9.8 from the textbook. So the basic question here is obesity related to incident cardiovascular disease? So is having obesity, does that increase or possibly decrease the risk of getting cardiovascular disease? Now, this is a question that we've looked at maybe in different forms before, and we've answered it in different ways. Logistic regression is going to be another way of analyzing our data. And so our data is given here in table 9.1, which is a data table that we've seen before, titled Baseline Obesity and Incident Cardiovascular Disease over a 10-year follow-up. So what they did is they enrolled 1,000 people in this study. At the beginning of the study, they recorded whether each person was obese or not. So we had a total of 300 obese people, 700 non-obese people. And then over 10 years, they recorded whether or not each person got cardiovascular disease. So we had a total of 106 got cardiovascular disease, 894 did not get cardiovascular disease. And the numbers in the center tell us the how many specifically in each group rather did or did not get cardiovascular disease. Okay. Now, so we have two indicator variables involved in this scenario. Remember, an indicator variable, we talked briefly or mentioned this term in one of the previous parts dealing with regression. An indicator variable is maybe another name for a dichotomous variable. It has either two outcomes. So in this case, we've got a variable of having cardiovascular disease, and that's our outcome variable. That's what we're really interested in predicting, is cardiovascular disease. And so each person either develops cardiovascular disease or they don't. So this is a dichotomous random variable, or we also call indicator variable. Likewise, each person is either obese or they're not. So obesity is another indicator variable, and that's our independent variable, or our predictor variable. So we're going to use obesity to try to predict cardiovascular disease. Now, because our outcome, cardiovascular disease, is dichotomous, we can use logistic regression to analyze our data. And so to kind of talk a little bit about the theory behind this, let's introduce some terminology here. So let's let p hat equal the probability of getting cardiovascular disease. Or we could think of that as like the proportion of people, of obese people who get to cardiovascular disease. And then the natural log of p hat divided by 1 minus p hat is equal to the natural log of the odds of getting cardiovascular disease. So this fraction here was another way of calculating odds of something happening. And then this is a natural log. And I remember from high school algebra, natural log was like the inverse operation of the exponential. And we're going to talk a little bit about the exponential here in a little bit. But you can start to see that the mathematics behind this logistic regression is very complicated. Another terminology here, x1, let that equal the variable of being obese. And this is a dichotomous variable. It equals 1 if the person is obese and 0 if not. So our model that we're going to use here is somewhat similar to the model that we used in linear regression. On the right-hand side, we've got this constant, or this intercept b naught, and then we've got this coefficient beta 1 and beta naught. So that looks very similar to the right-hand side of a linear regression equation. But on the left-hand side, we've got this natural log of the odds. And so this is the basic model for a logistic regression equation. The left-hand side is the natural log of the odds. The right-hand side is a constant plus a coefficient times our indicator variable. Okay. Now, when we do logistic regression, we're going to be able to do a hypothesis test on the value of this coefficient. And the hypothesis test is going to be very similar to what we did with linear regression. The null hypothesis is that coefficient equals 0, and the alternative is that the coefficient does not equal 0. Informally, the null hypothesis is that this indicator variable is not significant, and the alternative is that this indicator variable is significant. Okay. And so again, the calculations behind logistic regression are very complicated, so we won't even talk about how the numbers are calculated. We're just going to talk about what the results mean. So in table 922, they give the results from their logistic regression analysis. And so here we have the values of our coefficients. So this number right here is labeled intercept. That's in the approximate value of beta naught. And then this number here, 0.658, that's the approximate value of beta 1. That's the coefficient of the obesity variable. Okay. And so there's our regression coefficients. Again, very similar to what we saw with linear regression. Now in this column right here, we have the value of our test statistics for the associated hypothesis tests. Now this test statistic is labeled chi-squared because this is a value that comes from a chi-squared distribution. In linear regression, the test statistic came from a student t distribution, and so that test statistic was labeled t. Chi-squared we saw when we did the chi-squared goodness of fit and the chi-squared test of independence. Now this is a different type of hypothesis test than either of those types of hypothesis tests, but the test statistic comes from a chi-squared distribution. And then right here is the p-value for the associated hypothesis tests. And we're going to interpret those p-values in the same basic way as what we did with linear regression. And so basically the way we interpreted these p-values is that if the p-value was small, then that variable was significant. If the p-value was large, meaning greater than 0.05, then that variable was not significant. And so in this case, we see that both of these p-values are small. And specifically, we're more interested in the value of this obesity coefficient. That number is that p-value is small. And so that means that obesity is significant. So our conclusion here was that the association between obesity and incident cardiovascular disease is statistically significant, and the associated p-value is 0.0017. Okay. So again, this logistic regression is just another way of looking for a relationship between two variables. In logistic regression, our dependent variable or our response variable is always dichotomous. It has one of two values.